Every time you use something like ChatGPT or generate an image or even just use Google Translate, you're really seeing the legacy of one single revolutionary paper from back in 2017. Today, we're going to dig into that paper, Attention is All You Need. This is the story of the spark that really ignited the modern AI revolution.
Okay, so this quote, pulled right from the paper, it might seem a little dense, but it's the key to everything. It basically describes the big problem they were up against. Before 2017, AI models were just stuck. This inherently sequential nature they're talking about, it was a massive bottleneck, and it was holding back the entire field.
So, what exactly was this bottleneck? Well, back then, the best models for understanding language were called recurrent neural networks, or RNNs. And just like the name kind of implies, they had to process information in this really rigid step-by-step sequence. One word, then the next, then the next.
And you can really see the difference here. On the left, that's the old way. An RNN reading a sentence one word at a time, like a person reading a book. It's slow. And what's worse, by the time it gets to the end of a long paragraph, it might have already forgotten some of the crucial context from the very beginning. So the goal, which you see on the right, was to figure out a way to just shatter that linear chain, to process the entire sentence all at once. And this right here is where the breakthrough happens. A team of researchers over at Google came up with a completely new architecture. It was just a radical new way of thinking that would sidestep that whole sequential problem entirely. They gave their paper this incredibly bold, almost gutsy title, Attention is All You Need. I mean, think about that claim. They were basically saying you could throw out all those slow, sequential models and build something that was state-of-the-art using only a mechanism called attention. So what is this attention thing? Well, the core idea is honestly brilliant in its simplicity. It means that for any given word in a sentence, the model can instantly look at all the other words and figure out how relevant they are to each other. It's like it's asking, okay, to really understand this word, which other words in the sentence matter the most? And the amazing part is it does this for every single word, all at the exact same time. So this powerful self-attention mechanism is the absolute heart of the new architecture they introduced, which they called the transformer. All right, so let's pop the hood and see how this thing actually works. And here it is. This is the famous diagram from the paper. Now, I know, it looks complex, a little intimidating maybe, but the core idea is pretty simple. It's what's called an encoder-decoder model. The left side, the encoder, its job is to read and understand the input sentence. The right side, the decoder, takes that understanding and generates the output, like, say, a translation into another language. And right there, at the heart of both sides, you see that key component, attention. Let's actually break that complicated diagram down into 4 key steps. So first, words get turned into numbers the machine can understand. That's input embedding. Then, something called positional encoding gives the model clues about word order. Next up, you have the engine of the whole system, that multi-head attention. And finally, a feed-forward network just does a bit of final processing. Now, you might be thinking, wait a minute, if the model looks at all the words at once, how does it know that the dog chased the cat is different from the cat chased the dog? And that's a fantastic question, because this is where it gets really clever. The solution was to add a unique signal to each word, almost like a little numerical timestamp. This positional encoding tells the model exactly where each word sits in the sequence. It's how it keeps track of order without going one by one. So that basic attention calculation is already pretty powerful, but the transformer just supercharges it. Instead of just looking at the sentence one way, it runs several of these attention calculations at the same time, in parallel. This is what's called multi-head attention, and it's what lets the model understand text on a much, much deeper level. The best way to think about it is like having a committee of experts all reading the same sentence at once. In the original paper, they used 8 of these parallel heads. So one expert or one head might be focused on the grammar, another one might be tracking who is doing what to whom, a third could be trying to figure out what a pronoun like it refers to. By combining all of these different expert perspectives, the model gets this incredibly rich, robust understanding of the text. Okay, so the theory is elegant, the architecture is super clever, but did it actually work? This right here, this is the moment that lit the fuse on the entire AI revolution we're seeing today. So what we're looking at here are the results for a standard machine translation test. The metric they use is called a BLUE score. All you need to know is that higher is better. You can see the previous top-of-the-line models are hovering around 26.3. And then the single transformer model just comes in and completely smashes that record with a 28.4.
Now, a 2-point jump in blue score might not sound like a huge deal to you or me, but in the world of machine translation research, that is a monumental leap. This isn't just a small, incremental improvement. This is the kind of result that makes the entire research community just stop what they're doing and pay very, very close attention.
And here's the real kicker. It wasn't just more accurate. Because of its parallel design, it was dramatically faster and cheaper to train. It got these new state-of-the-art results using just a fraction of the training cost of the older models. So you have better results in less time for less money. It was a total game changer. The impact was, well, immediate and just profound. This architecture basically became the blueprint for almost every major AI advancement that came next. In 2018, it led to Google's BERT model. Then came OpenAI's GPT series. And now it's the foundation for the entire explosion of large language models that we're all interacting with today. They were all built on the ideas in this paper. So when you boil it all down, that one big shift from sequential word-by-word processing to parallel all-at-once attention, that was the key that unlocked the door. It made it possible to train AI on vastly larger data sets than anyone had ever dreamed of, which is what enabled the massive, powerful, and sometimes really surprising AI we see today. The attention is all you need paper found a fundamental bottleneck and just shattered it, proving that a single elegant idea can completely change everything. And that leaves us with a pretty fascinating question to think about. What's the next big bottleneck holding AI back? And who's going to be the one to break it?